Welcome to the Explainer. So, there is a fundamental architectural mismatch that's just been quietly growing in modern enterprise software. And as autonomous AI matures, which, let's face it, is happening at a totally breakneck pace, it is forcing a massive shift away from our traditional databases. We're literally moving from static, passive storage to this high-velocity, always-on, agentic action.
To really get why this matters, let's look at a pretty fascinating historical parallel. Think about the Jacobite Rising back in 1745. That was a fierce, super dynamic rebellion against a deeply entrenched, rigid establishment. Well, today, we're witnessing a very similar tech rebellion. Our legacy databases? They are that rigid establishment. And these new, event-driven, dynamic AI networks are the uprising. They are actively challenging those static, forgetful systems that, honestly, just cannot keep up with the intense demands of modern autonomous agent fleets.
Here is our cognitive roadmap for today. 1. The rigid status quo. 2. The rise of the metanet. 3. Graph-native agent memory. 4. Event-driven AI architecture. And 5. Sovereign on-chain identity.
Let's jump right into Section 1, the rigid status quo, focusing on legacy databases.
Let's start by looking closely at our establishment, right? The traditional database systems and static neural networks that have dominated our landscape for decades. The contrast here is actually pretty stark. Historically, databases were built as passive systems of record. They just sit there patiently waiting for explicit human-scale queries to spit back static data sets. But agentic systems, they toss all of that right out the window. Today's autonomous fleets are running continuous decision-making loops at absolute machine speed. They're multiplying query volumes by factors of 10 to 100. That demands an architecture that is active, persistent, and can actually handle totally unpredictable goal-driven swarms.
And that brings us to a huge vulnerability in the current AI setup. Traditional LLMs are inherently stateless. When you rely purely on vector similarity matching for memory, well, the system basically just retrieves what sounds similar, rather than pulling what is structurally relevant based on a user's entire history and evolving state. Basically, vector memory degrades really fast.
Which leads us to Section 2, the rise of the metanet, our new architecture. This is the real threat to that rigid status quo. It's a completely new architectural foundation called the metanet. If you look at U.S. Patent 12,664,142, it maps biological terms directly to this tech in a really brilliant way. Instead of a classic neural net where you have fixed graphs and learned weights that are just locked in during training, the metanet operates as an actively evolving graph of agents and services. So a biological neuron becomes a script node. A synapse becomes an API, and learning isn't just tweaking some numerical weights anymore. It's the actual structural growth of a hierarchical script database.
The crucial takeaway here is that within this tree database, nodes are not just passive containers. They actually contain both data and function properties inside an interpreter environment. So when an event hits, a node can literally spawn a brand new child node to hold that incoming data. Your AI agents are actively evolving by adding entirely new branches and executable state to their knowledge structures right in real time.
Moving on to Section 3, Graph-native agent memory and agent capabilities.
To actually support these evolving script nodes, we need a memory system that operates at machine speed. As we just talked about, vector memory forgets, but graphs don't. We have to move away from the amnesia of isolated vectors and adopt a unified, native graph. This is what lets an AI system reason over its entire historical context instantly without losing the structural why behind the data.
To build a truly complete cognitive profile, memgraph breaks memory down into 3 interconnected types. You've got semantic memory, which holds your static facts and entity knowledge, the what the system knows. Then episodic memory tracks past interactions and temporal context, the what it experienced. And finally, procedural memory handles decision trees and workflows, the what it knows how to do. In a graph, these aren't isolated at all. A semantic fact connects directly to an episodic event, which then triggers a procedural response. It's a multi-hop relationship that standard vector databases literally cannot represent.
Now you might be thinking, why not just use a standard relational database for this? Well, tracking dependencies between all these different memory types in a relational system requires incredibly complex junction tables and multi-join queries. As you go deeper, the required compute power grows exponentially. It's a nightmare. But in native graph databases, relationships are first-class citizens. Dependencies are literal directed edges. The structural primitives of a graph natively track these multi-hop dependencies in what's called O of one time, meaning it happens almost instantly, no matter how massive the dataset is. You can traverse these complex webs of logic in milliseconds.
Okay, Section 4, Event-Driven AI Architecture and Machine Speed Action.
So how do these MetaNet agents actually communicate and take action out in the wild? That takes a shift to an event-driven architecture. Instead of agents constantly pulling databases and burning through compute, they use a Kafka-compatible backbone. Imagine an event producer emits a signal at t+0 milliseconds, say a data quality alert. The event bus instantly routes it by t+15 milliseconds. And by t+30 milliseconds, multiple subscribed AI agents consume that event simultaneously in this massive fan-out pattern. They're operating in a non-blocking loop, reacting asynchronously the exact millisecond a relevant change happens in their environment.
Of course, these agents actually need to understand the database they're interacting with. In the past, we relied on super fragile text-to-SQL prompt engineering. And honestly, that just led models to hallucinate table names and crash servers. Enter the Model Context Protocol, or MCP. This acts as a standardized universal gateway. It predictably maps natural language to structured graph operations using schema-first navigation, totally saving us from those fragile prompts.
And these event streams aren't just built for pure speed. They fundamentally solve a massive governance problem. Think about it. Agents acting on ungoverned context create outcomes that nobody can explain. But by maintaining a Kafka-backed metadata changelog, we can answer the most critical debugging question in AI. What exactly did the system know at that exact moment? We can perfectly reconstruct an agent's knowledge state to ensure true, verifiable intelligence.
Finally, Section 5, Sovereign On-Chain Identity and Cryptographic Trust.
As these highly capable agents fan out across the network, we have to establish treaties and trust. Every single agentic action needs to be cryptographically secured and totally traceable. So behold the SIS-01 Identity Trinity. Based on the ERC 7827 standard, identity in the MetaNet isn't just some isolated NFT, it is a 3-shard stack. You have the MindPipe using ERC 8004 for a global namespace. Then, Island Hats manages your hierarchical permissions, and the individual cell represents the specific agent instance. This setup literally bifurcates the agentic soul into interoperable layers, giving us bit-perfect backwards compatibility without ever relying on centralized servers. And to make this whole swarm economy actually function, we bring in economic middleware. The X402 protocol steps in to solve API key debt through decentralized micropayments. High-fidelity agent actions, called strikes, are monetized completely seamlessly using USDC on Layer 2 networks. Plus, click-wrap binding ensures that sovereign legal agreements are tied directly to these on-chain identities. This is absolutely crucial because it guarantees deterministic halting. We're moving away from the lossy, probabilistic guesses of modern cloud systems and moving toward bit-perfect, verifiable human intent.
So as we watch this massive shift from passive storage to high-velocity action, it is clear that the rigid status quo is crumbling. By combining dynamic script trees, graph-native memory, event-driven buses, and sovereign on-chain identity, this MetaNet architecture is completely redefining verifiable intelligence. I'm going to leave you with this to ponder. When this entire database revolution is finally complete, what will your agents actually remember? And how exactly will they act on it? Thanks so much for joining me on this explainer. Keep learning, and I'll catch you next time.